Based on my 5 minutes.
Based on your 5 minutes. Okay, thank you everyone. Today we're especially pleased to have Marianne back. Marianne did her PhD and undergrad here, PhD. All the way through, yes. All the way through. So proof that it is possible, like myself, I did all my degrees here as well, to come back. So just in case people were thinking that you have to go to your graduate studies somewhere else in order to come back, no, it is possible, but it's more exceptional, which is why we have an exceptional person with us today. Who's going to give an exceptional talk. Let's really play this one.
No pressure.
No pressure. We'll really build it up. So I'll ask you to join me and welcome Marianne.
Thanks very much, Greg. And yeah, thank you everyone for having me. I'm really excited to be here. It sounds like I don't have perimeter here. I'm not sure why. So yeah, I'm just here today to tell you a little bit about some of the work that I've done over the last few years and what's led up to this new research program that I'm trying to build here at UT. I started in July, so a couple months in at this point. I'm cross-appointed between civil and mechanical engineering, even though I came through the civil side here doing my PhD and my undergrad. So before we get into the outline for today's talk, though, I'm really excited because I get to talk about my favorite thing today, which is MURBs. I don't know if anybody's heard of MURBs before. When I say MURB, I mean multi-unit residential building, just up the top there. I think this is a really, really interesting type of building that has a lot of unique problems, and that's why most of my research career thus far has been spent just focused on this particular area. These buildings are very distinct from single-family homes, which is where when we talk about residential buildings, what most people would think of. But it's also very different from commercial high-rise buildings. We have all of the challenges that we would see, if not more so, that we see with high-rise buildings, but we have that occupant wild card. These are people's homes, and they can choose to do almost whatever they want in their own home. They can operate their windows, they can cook, there are a lot of activities that we see in these buildings that are different from other high-rise buildings. So just a bit of context why I think these are pretty unique and interesting to study. Oh, maybe the mess doesn't work for advancing.
Let's hope.
Here, I just don't want to stand on the other side. Okay. Oh, I think it's just really sluggish, actually. Sorry. Anyway. Whoop. I apologize. I think I clicked it too many times thinking it wasn't working. Let me just think back here.
Oh, it's an apple, I think.
Well, no. Anyway, this might bop around a little bit because now I've hit it 5 more times, so we'll see what happens. So today I'm just going to start out with an overview of some of the characteristics of multi-unit residential buildings. And I've split this up into 2 categories, both old and new. And the reason for that is the chart that you see along the bottom there. So after the Second World War, we saw a huge boom of multi-unit residential buildings in the 1960s and 70s, which, sorry, I don't have a pointer here, but anyway, right around here. So Toronto is not completely unique, but we do have, unlike most North American cities, we have a really, really high concentration of these buildings. And you know, we're a number of decades on now in their service life, and so we have a lot of operational issues that we need to deal with respect to this particular population. But as you can see on the right-hand side, we're actually, and as you can see all around us with all the tower cranes that are going up just south of here, we're in the midst of a second boom. So I'm going to try to talk about both of these groups separately, so the 1960s, 70s cohort, and then the newer condominiums that we're seeing now. So the framework for this talk will really be about energy retrofit. The reason why I'm going to focus on retrofits is because building renewal rates are quite low. So we're looking at maybe 2% a year on average as our new part of our building stock. So most of the issues that we have to deal with in this sector are related to our existing buildings. But the lessons that we learn from our existing buildings, we can actually apply in building design. So we're kind of or not supposed to use killing 2 birds with 1 stone anymore. What is it? Feeding 2 birds with... No, it doesn't work. Okay. And then, so after we talk a little bit about energy retrofits, we're going to talk about why it shouldn't be all about energy, and that will lead nicely into why this new lab exists, or the program that I'm trying to grow here, which is really at the intersection between building energies and indoor environmental health. So, oh, sorry guys.
I don't know why it's so sluggish.
I don't know if I'm doing it right. I just don't want to click it too many times.
Yeah.
So. And I do have a lot of clicks in this presentation, unfortunately.
Use the arrow keys, correct?
Yeah, that's what I'm using, but then they sort of skip ahead. Okay, so, okay, yeah, sorry, I guess the arrows are a little more responsive than the mouse. So we'll use that.
Oh, that's cool.
Whoa, okay.
Whoa.
Anyway, so when I talk about these older buildings, I'm referring to these, I mean, you see them all over Toronto, these primarily very thermally massive concrete buildings that we see built in the 1960s and 70s. I'm going to talk about them from the social housing context. The reason why is because social housing organizations will typically own a large population of these buildings, and so we have more data from these larger landlords, whereas when you're trying to characterize some of those individual private rentals, that's a little bit more difficult. So a lot of the stats that I'm going to show with respect to the older buildings are actually related to community housing or social housing. So first of all, as we saw, I mean, these were all built in the 1960s and 70s. These buildings are pretty old. We've got a huge stock, about 1,200 in the GTA and over 2,000 in Southern Ontario of these buildings that are built between the 1960s. They also use a lot of energy. They were built at a time when energy wasn't really a consideration in design. But what's of greater concern is the proportion of energy costs relative to the income of the people that are living in these buildings. So it is a much more significant part. And this isn't just in Toronto. In a lot of the Toronto buildings, it's actually rolled right into the rent. But when we look at some of the European models where the residents actually pay for their utility bills, this can lead to fuel poverty, and we'll talk a little bit more about that later on. They also aren't terribly well maintained. There's just a huge backlog. There's a tremendous amount of work that needs to be done to these buildings, and it hasn't been done in a timely fashion, and so now we're running up against a huge backlog. They also have a lot of issues with their indoor environment, air quality issues, thermal comfort issues as well. And we have a lot of them. So as I threw out a few numbers before, but just to give you a context of how that fits into the overall pool of rental stock, we're almost a third of the rental stock is provided in Toronto by these social housing buildings. Okay, the slide is transitioned. I think, maybe not. There we go. There we go, blast right ahead. Okay, so let's contrast that with our newer condos. So the condos that we see to the south of us, highly glazed. In Canada's 3 largest cities, they make up almost 20% of our households and provide over a third of new housing in Canadian cities. That's projected to increase to about 50% of new housing over the next 20 years. So this is an area that we need to start paying more attention to. Huge value tied up in these assets, so we don't want to necessarily end up down the same path that we have with these 1960s and 70s buildings. We want to stay on top of the maintenance issues. Now we have the opportunity. These are very new. So the other problem is, though, we have very limited data on how these buildings are performing. And so that's one of the things that I'd like to address with my research program. But in one of the very few studies that was done based on some of the Toronto buildings, these are actually 2 quotes from a survey within the same building. So the first one is, it's always hot in the winter. They had to take all of these measures to try to control the overheating. They installed blackout blinds. They leave the windows open all the time. In the same building, you have people complaining that it's too cold. It's always drafty. We've got ice buildup. So there are obviously some significant control issues happening here. But we don't have a lot of information about those problems yet. Okay, my advanced slide in advance of my talk. So this is some data that I actually collected during my PhD. that looks at a sample of MURBs across all voltages and how variable their energy use is. And really what this was pointing to, there are a lot of similar characteristics between these buildings. So one of the hypotheses was that maybe some of this was related to how we operate the building. And other jurisdictions have found similar findings. In New York, which is the next slide, they've had benchmarking regulations in place for the last couple of years, and so they've got this wonderful wealth of data about all of their buildings, both energy use and water use. And what they started to, I'm sorry, I apologize, all over the place right now. Anyway, okay, we'll just leave that for now. So basically the findings from the New York study were similar. They were hugely variable, and so they started to wonder, okay, so they're actually, if we separate out all of the variables like fenestration ratio and boiler efficiency and all of those other building level characteristics, there's still variability that we really can't explain. And so the thought there was that it's really how we're operating buildings and how these occupants are interacting with those buildings. And so on the previous slide, it was just referencing a study that was done by some of the folks in Ryerson, that was where those survey quotes came from earlier, and they found something like 60 to 70% of the variability in heating and cooling loads they could not attribute to the building characteristics. It was purely to building occupancy. So, and this is something that I feel is quite unique with MURBs. The occupants really have a lot of control over their buildings compared to other commercial buildings. So now that we have sort of an overview of the issues and the data that we've got in both of these sectors, I just want to give an overview of the energy retrofit process and some of the I guess, the thought process that we would go through as we're preparing for an energy retrofit. Unfortunately, a lot of times an energy retrofit is driven by a failure. So we leave it until it's too late, and then that equipment has failed. Occasionally, we start to try to anticipate, oh, we're getting to the end of the useful life of this particular boiler. Occasionally, it's driven by a need to reduce operating expenses, and also incentive programs can also be drivers, and we're going to come back to that a little bit later, because as we see things like energy reporting requirements and a price on carbon, I think those incentive programs are going to start to become more comprehensive. So as a result of the need to reduce operating expenses and some of these incentive programs, we end up often just scooping up that lowest hanging fruit. So lighting retrofits and water retrofits or water fixture retrofits typically paybacks within under a year, so they're absolute no-brainers. But once you've sort of scooped up those quick payback periods, then it makes it harder to pay for those larger items. So really, there's a growing recognition of the need for a more comprehensive approach to retrofits, where you can actually balance some of those quick payback periods with some of those larger ticket items like window replacements, boiler replacements, things like that. And we're also starting to recognize that piecemeal approach that we've taken up until now, it takes longer, it's more expensive, you have to go through the contracting process multiple times. So there are now new financing vehicles that are being developed to try to support building owners in taking that more comprehensive approach. Prior to joining the faculty here, I was working with the Toronto Atmospheric Fund, which is now the Atmospheric Fund, because they've expanded outside of the Toronto region. And they are one of those organizations that's really working on trying to promote these new financing vehicles. But in addition to this, by just replacing those single component items, there are limits to the efficiencies that we can get from a change to one component. So really the benefit of having a more comprehensive approach is we can start to change the way the building is operated or significantly change the loads. And with improvements to the envelope, we can also significantly reduce vulnerability to changing utility prices and vulnerability to a changing climate as well. We're seeing more extreme weather events also. I did hit something. Okay. So just to give you a sense of where all this energy is going and what we're trying to tackle here, this is just a typical distribution of energy use in Canadian MURBs. We're a heating-dominated climate, so it makes sense that most of our heating, about half of it, goes towards space heating, but a quarter of it goes towards water heating. And the red and magenta parts of the pie are primarily provided by natural gas, which is much higher greenhouse gas emissions per equivalent kilowatt hour of energy. So really when we start to talk about meeting stringent GHG targets going forward, it's those two big pieces of pie that we're targeting. So we have a lot of work to do because we rely on natural gas pretty heavily in the residential sector.
While we're waiting for it, are these buildings actually air conditioned? I'm amazed at the space cooling being 1%.
So most of the rental buildings, like most of those older buildings, do not have central cooling. So they've got those little window shakers. But in the newer buildings you see down here, they absolutely have to. They're greenhouses. So, but yeah, it's still pretty small. So let's just pick apart that that heating energy piece of the pie, or that natural gas part of the pie, because that's really the one that we're most interested in as we're trying to reduce energy use. So there's really two components to this. I'll just describe this graph first. I'm going to click through some of these that we've got. Oh, see, now it works. Anyway, that's fine. So on the y-axis here, we've got our monthly natural gas consumption, which you would just get from your utility bills, and on the x-axis at the bottom there, we've got monthly heating degree days. For those that aren't familiar with, who's heard of a heating degree day before? A couple people. Okay, so for those that haven't, it's kind of a wacky unit that we use in building energy research and building energy work. It's basically an indication of how much heating or cooling a building would require. So imagine it's the difference between your interior temperature that you would like and wherever your outside temperature is, whether it's below that desired temperature or above. And then it's simply integrating the area underneath that curve. So you're looking at the delta T over time and how much energy you're going to need to get to that desired temperature. That's all that indicates. So, so typically what we do to understand how a building behaves with changes to the outdoor conditions is we would plot our energy use over our heating or cooling degree days, although there are issues with that. So there are really two components. So our base load component, which is representative of that fuchsia piece of the pie, that domestic hot water load, that's relatively constant. It changes a little bit with occupancy. But the piece that we're really interested in is that variable load component, which is influenced by our building envelope and our heating. So HVAC up there is heating, ventilating, and air conditioning equipment. And so that's the one that we can really influence with retrofits to our building. Okay, so I'm just going to, oh, it's there. So I'm just going to talk a little bit more about the influencing factors of that variable piece of the pie. So envelope thermal resistance, air leakage, and equipment efficiency. So this is just a schematic of these, oh, we went like right past this. A schematic of these older post-war buildings. So typically very little insulation. It's just a block backup wall with a brick veneer. Really great thermal bridges through these exposed slab edges, really effective heat loss or heat transfer mechanisms. And they often have their existing or their original single glazed windows, sliders, aluminum frame, not thermally broken, terribly energy inefficient. And the windows are really the weakest part of our building envelope because, well, for a number of reasons due to air leakage and conduction. But on the right here is what we're building right now. All windows. All windows. Right? So, so I don't know if we're really learning any lessons from the performance of our older buildings when it comes to envelope performance, but we'll talk a little bit more about that. Air leakage was really the big one, though. I'm just going to click all the way.
Yeah, it's amazing that those buildings, if you were to design a cooling system for electronics, it would look exactly like that.
How do you maximize heat loss?
How do you maximize heat loss? You put lots of fins.
Yeah.
Exactly.
Yeah. So air leakage is a really complex topic, specifically when you get into high-rise buildings. There are a lot of negative impacts, building durability when you're bringing in warm, moist air coming into contact with colder parts of the building envelope, thermal comfort issues, air quality issues. And there have been a number of studies to show that the ways in which we ventilate these older buildings using corridor pressurization. So you essentially have an air handling unit on the roof that's drawing in fresh air, conditioning it, and pushing it down into the common corridors. Ideally, in a perfect world, it's creating a positively pressurized space that prevents cross-contamination between suites when you open those doors, because the air should be rushing in or underneath those door undercuts. But because the effects of wind and stack quickly overwhelm the mechanical pressures created by those air handling units, we know that these systems don't work very well now. So one of the big challenges is how do we deal with these existing buildings? And the way, I mean, in new buildings it's a little bit different. They're ducted right into the suite, but we're still dealing with that fight between mechanical pressures and wind and stack. And it's not an insignificant part of the load. So, so one study showed in Ontario, 25 to 40% of the peak heating demand is related just to air leakage. So of that 50% of the pie, that's a big chunk just related to this air leakage. And one really interesting study in Vancouver that was looking at distribution of ventilation air through the building. This is a milder climate than ours, bear in mind. Almost 70% of the energy that went to space heating was used to condition the ventilation air. But only a fraction of that was actually getting to the suite. So we're wasting a ton of energy here trying to condition this air, but then it's not getting to the places where we need it to go. So we need to be, and I'll talk about some of the ways that we'll address this, but we need to be, be more careful about how we direct all of this conditioned ventilation air to the spaces where our occupants actually are. And then the last one I'll just start talking about already is HVAC equipment efficiencies. So again, a lot of things affect this. In energy modeling, we typically just use the rated efficiency of a particular piece of equipment, but how that piece of equipment is connected to the rest of the building makes a big difference, how it's maintained. The study that I was doing during my PhD was trying to correlate boiler efficiency with that variable natural gas component. So how does the efficiency affect that amount of energy that we spend on space heating? And you can see the correlation is terrible. I mean, we can't really rely on these rated efficiencies. So TAF, the Atmospheric Fund, is currently undergoing a fairly long-term study. We have about 1.5 years worth of data right now for the heating plant efficiencies of 10 buildings. So that will go a long way to helping us understand the difference between the rated efficiencies that we see and how these buildings are actually performing. So as we're approaching energy retrofit, there are a few things that you need to do. You first need to figure out where you're at. So establish a baseline level of energy performance, develop a model. We'll talk about each of these in more detail, so I'm going to go through this a little bit quickly. Determine the potential savings and set targets, so where are we trying to go, and then and select a strategy that meets those targets. So with our baseline, we can use a number of different tools for this. So we'll often go out to the building and have a look at the conditions of the envelope and the HVAC systems. We'll gather as much historical utility data as possible. This is getting easier to do with building automation systems, but oftentimes it involves bugging the property manager for all of their old electricity and natural gas bills. And then we can, that's typically where that stops, that investigation, but there are some other things we can do in terms of assessing building envelope performance with air leakage testing and infrared imaging, and then if we want to go further, that's sub-metering. And then we can use all of this to start to develop an energy model, which we would use to test various different retrofit strategies. So, but one of the things that I found when I was working on my PhD was that there, and I mean, this is well understood in the modeling community, there are a lot of really big question marks on some of the data that you're putting into these models. So if you think back to our energy pie, so our red half space heating energy. It's influenced by a lot of different factors. So boiler efficiency, which we've already established, the rated efficiencies are not a terribly good indication of the variable natural gas consumption. Air leakage is a huge unknown. So the graph on the left here is really just exploring those uncertainties. So without knowing what our boiler efficiency is, we had rated efficiencies for the red building and for the blue building, but we recognized that there was a lot of uncertainty there. By calibrating the model with just those, tuning the dials on just those two parameters, you can get hugely varying air leakage rates from a super tight building to a super leaky building. So what are we using these models for? If we're not able to get a better handle on probably the two parameters that influence the largest piece of the pie the most, I mean, it's garbage in, garbage out. We need to have a more comprehensive approach to assessing these parameters and making sure that our models are more reliable. The example on the right is just a comparison of an energy model. On the red line at the bottom there is just the default temperatures. So what the model would have, if you left the defaults as if, what the model would have predicted were the interior temperatures. But I had actually gone and monitored this building over a year and looked at what the interior temperatures were and found that they were actually quite different, about 4 degrees difference during the winter months. So, so gathering that additional field data is really important to calibrating models.
Are those air leakage rates actually, those are realistic values?
At the bottom?
Yeah.
Yeah. I mean, they're at, sorry,
Don't go back.
I can't remember what, no, sorry, I won't go back.
But they were 0.1 to 0.4, that's almost half a foot per minute or quarter foot per minute of velocity. That's kind of a phenomenal.
Well, I'm trying to think now whether those were ambient air change per hour or put in units on the bottom. I don't really remember.
Anyway, we'll ask you this.
Okay, so we've just passed through a few different. Doesn't matter. We're just going to skip right over this section.
Yeah.
Oh dear. Okay. I mean, generally speaking here, and you're done. Okay. I mean, generally speaking, the approach when you're looking at these energy retrofits, I mentioned taking a more comprehensive approach rather than just gathering that low-hanging fruit, is to look at how the passive and the active measures can complement one another. Oh, now it's just going on its own. And so recognizing that changes to the envelope can really have a huge impact on our heating and cooling loads, but we don't necessarily want to undertake an envelope retrofit and then have our mechanical equipment be dramatically oversized. So you really need to look at those things in parallel. So, I mean, you can stop here and you can just do your energy analysis and carry on without any consideration for the occupants in the building. But why do we have buildings? I mean, we don't have buildings for building's sake. We don't have buildings to improve building performance. We have buildings to provide homes for people, to provide productive places for people to work, to provide healthcare facilities, to provide learning facilities. That's really the main purpose of building. And so we can't really undertake these retrofits without considering the people that we're designing buildings for. And so that's really the direction that we're trying to move in. Because it's important to recognize that it's not that all energy retrofits will have a negative impact on the quality of the indoor environment. There are certainly synergies, but they need to be considered because they could potentially have negative impact. And So the two main lenses, I guess, through which we want to look at that indoor environmental quality are considering occupant health and also occupant comfort. So we spend most of our time indoors, and of that time that we spend indoors, most of it's spent at home. So these are really important environments that we should be considering. With respect to MURBs, I mentioned earlier, occupants are really the wild card. They can do whatever they want in their apartment. In most buildings, you can still smoke. And you have often direct pathways between suites through uncontrolled air leakage between those apartments. And so that's a really, really common thing in these buildings. Odor transmission. But with that odor transmission, where there's air, there's sound transmission. There's also the potential for pest transmission between suites. So we need to be considering all of those elements. And comfort, we've spent a lot of time talking about thermal comfort in the commercial context because it has a direct impact on the productivity of your worker. But we spent a lot less time considering that for the residential context. And I think that's something that we need to turn our attention to. As we've seen some of the anecdotal evidence in these newer buildings, thermal comfort is a huge problem. But as I pointed out before, there's also that economic issue as well. So where you have really high energy prices, you can actually have people underheating their buildings just to be able to pay the rent to buy groceries. And so that trade-off shouldn't make sense. You should be able to have a comfortable indoor environment. But what we found, these seem like contradictory results, but they are in different areas. These would apply differently, and even in the same building, as we saw, at the lower half of the building you can have underheating, and at the top of the building you can have overheating. But overheating is becoming a really serious problem because as we see the increasing frequency and length of extreme warm weather, hot weather events, we're going to start seeing more issues related to overheating of these buildings. So there was a study that we did with, this was right after I finished my PhD when I was working for the Toronto Atmospheric Fund. We started a study with Toronto Community Housing that was looking at monitoring the indoor environmental quality parameters and energy of 7 different buildings across 3 different sites. Actually, Professor Siegel is involved in that study as well from the indoor air quality perspective. So what prompted this study was that they were undergoing a series of comprehensive energy retrofits in these 7 buildings. And this was a great opportunity to get a sense for how those indoor environmental parameters change before the retrofit to after the retrofit. So the retrofits have actually just been completed. So there's over a year's worth of pre-retrofit data, and then the study will continue on from now to look at that difference between pre and post-retrofit data. So it involves a lot of different parameters: temperature, relative humidity, mean radiant temperature, and then the indoor air quality parameters, concentrations of CO2, radon, formaldehyde, and then particulate matter sampling as well. And then this is related to the boiler efficiency monitoring that I spoke about before, and that's going to be really, really useful data to see what the real-time efficiency of these heating plants are. And what was great was we also had an opportunity to do occupant surveys. So in addition to just collecting this objective data at the suite level, we also had an opportunity to ask the residents how they felt about being in these buildings. And what we found was kind of surprising. So on the next slide, we've just got some of the data from the summer months. And I mean, the indoor temperatures were extreme, almost 28 degrees on average. That's not maximum during the summer months. And over 50% of the residents were complaining about being too warm. So really extreme overheating. These are very thermally massive buildings, so they aren't necessarily benefiting as much as they could be from diurnal temperature swings during extreme heat events. The buildings just don't cool down, just sort of keep heating up. And where these buildings house a lot of vulnerable residents that aren't necessarily as mobile as people in other communities, so this can have significant health impact. And what we found from this study, we were asking residents about their use of fans and air conditioning units. And despite using an air conditioner daily, a large proportion of the respondents were saying that they were still too warm. So these mechanical interventions have a huge energy penalty, but they're not even necessarily helping us achieve that desired comfort level. So we need to start rethinking how we create a comfortable environment in the building. And that's where we can start to look at passive approaches. The next slide is just looking briefly at, okay, I think we passed right over the next slide, but that's okay. So one of the interesting things that we found about this study, because we were on 3 different sites, there are 3 very different populations. So one is mostly families, one is bachelor units, and one was senior. And it was funny because comparing the objective temperature data to the subjective survey data, the seniors were like, we're fine, no problem, and these are the warmest buildings in the whole study. Whereas the family buildings at the other end of the spectrum were the more moderate. We were seeing more moderate temperatures in the summertime, but they were the ones that were complaining the most. They were uncomfortable. So it's not just collecting the data in the suite and making decisions about the temperatures that we see. We need to be engaging the resident in that conversation as well to sort of contextualize the data that we're seeing. This is really just expanding on what I was talking about before, that increased risk over the coming years as we start to see greater extreme heat events. We saw similar results in the wintertime as well. Average temperatures of well over 25 degrees in the middle of winter.
They're heating 20, not intentionally, I guess.
No, this is overheating. So basically, I mean, anecdotally, what I'm hearing from building owners, building managers, is there's a complaint. Oh, sorry, this is the graph that I was thinking. Nobody is ever complaining that it's too hot. They just open their windows and use that to finely tune their thermal comfort. But they get complaints when it's too cold. So at the beginning of the winter, they had the boilers set appropriately. But then with each complaint about it being too cold, they go up and up and up and up, and they don't go back down. So we're sort of increasing our overheating as we progress through the winter. So anyway, we've already talked about this, so that's fine. I think I'm just gonna skip ahead because I'm just going to skip right ahead to some of our lab projects. I realize we're kind of running out of time here. Anyway, I mean, what we're going to just flip through really quickly is some of the changes that we need to make to our current approach to retrofits. We need to do a better job at getting a sense for what's happening in the buildings beyond just that energy submetering. So some selected in-suite monitoring during shoulder seasons. Don't worry about this. We're just going to look right through here. During shoulder season and short-term monitoring in the winter and the summer to get a sense for the magnitude of some of these thermal comfort issues. Occupant surveys are really, really important. Pre-retrofit to understand what some of the important issues are. Anyway, so this whole experience through my PhD and through the work with the Toronto Atmospheric Fund is what really got me interested in that intersection between the quality of the indoor environment and what we and how we're using our energy. So, okay, I'm not going to worry about this anymore. We're just going to talk about some of the projects that we're working on. So really, the work that we do in this lab is really at the intersection of HVAC system performance, building envelope performance, and occupants, and how all of those pieces interact together. So sometimes things are a little messy, and so it's sometimes difficult to get to the root of the problem because you're trying to figure out, is it a mechanical issue, is it an occupant issue, and so combining this use of occupant surveys and interviews with this more objective environmental monitoring with energy submetering are really all of the tools that we have in our toolbox to start figuring out what some of these issues are. So some of the projects that we're working on right now are, one is really that intersection between occupants and the HVAC system. So it's focused on the performance of heat recovery ventilators. So has anybody heard of the heat recovery ventilator? So we're seeing these units installed more in newer condominiums. And so transitioning away from that central ventilation system that I described at the very beginning to suite level ventilation. So each condo unit or apartment has their own heat recovery ventilator that supplies a balanced fresh air and exhaust air to the outside. But the consulting community is starting to see, we're starting to receive complaints of cross-contamination between those suites, because rather than having a single exhaust or two exhausts on the roof, you now have a bunch of exhausts coming out the side of the building. And so depending on the direction of the wind, you might have air coming out one suite and being drawn into the next suite. And so the project that we're working on right now, it's a couple of different aspects to it. One is interviews with the consulting community to get a better handle on how they currently approach these problems, and then develop a standard test method to use in the field that consultants can use to consistently assess whether or not this is actually a problem and to what degree. Another project that we're working on is related to occupant and also HVAC system control, actually. So we're working with Ecobee, which is a Canadian manufacturer of smart thermostats. They've done a lot of work in the single-family home sector, but we see a lot of potential for use of this technology in the multifamily sector, particularly because you can combine them together as a network and manage peak load demand. So I hope in the next couple of weeks, actually probably the next 2 months or so, we're going to start a pilot with a condo downtown here, installing a number of smart thermostats and switching the smart capability off and on. So it will operate like a regular thermostat sometimes and a smart thermostat other times. Ideally, the occupants won't be aware of any changes, and we're going to monitor any perceived changes through occupant surveys. But ideally, what we're hoping to get out of this study is what sort of energy benefits can we expect from the use of this technology at the building level, ideally with no negative consequences for the occupant experience. Another study that we're looking at is the other piece is related to some of the energy model uncertainty that I was talking about earlier. So one of the big pieces, as you all appreciate now, is air leakage. And conducting air leakage testing in a multifamily building is very challenging because you need to isolate the suites all around the suite of interest and neutralize the pressure difference. So you basically need access to 9 people's apartments for an extended period of time. There's security issues there. It's just disruptive, it's expensive, it's time consuming. So what we're trying to do is target the part of the envelope which we know is the weakest, which is the envelope, which is the window, and focus on window air leakage testing, which we only have to disturb one occupant to do at a time. And then we're using that to calibrate new energy models to determine what the air leakage through the wall components are. So we're trying to develop ways that consultants can do a better job of getting some of this important data that they need pre-retrofit without being too time-consuming or expensive. So that's really the objective there. And then the other piece, especially in the multi-unit residential buildings, is window operations. So in commercial buildings, you're often hermetically sealed. You cannot open those windows. But we don't have a great understanding of what drives occupant behavior in terms of window operation. So we're also doing a study on using different sensors and techniques. What's the best way to conduct a large field study of window operation? So we're also working on that. So that's just a little flavor for what we're doing. I thought I'd leave you on the last slide. So those are the projects that we're currently working on, but what I'd like to start moving towards in the next couple of years is a similarly large field monitoring campaign to what we've done with the social housing buildings, but in these new condos. We really have very little information about what's happening in these buildings, and I think we need a similar scale study to really understand the relationship between energy use and indoor environmental quality there. Another fun plug, I think I'll just conclude on this because I realize we only have a couple minutes left, and there might be some questions. We also are building a new lab on the roof of the Stanford Fleming building, which will have 2 twin suites, and we'll be able to test there are a number of different HVAC systems, there are removable envelope components, and finishes that will allow for indoor air quality testing as well. So Professor Siegel and Professor Russell and I will be able to use that facility to do a number of different studies related to HVAC, thermal comfort, indoor air quality, envelope performance. So we're really excited about that as well. So I apologize for how disjointed this was, but if you're able to make any sense of it, I'm happy to take any questions right now. Also happy to carry on the conversation beyond this. So.